A uniform stick that's 2 meters long with a total mass of 16.4 kilograms is pivoted at its center. A 4-gram bullet collides with the stick midway between the pivot and one end, and it is shot perpendicular to the lever arm. The bullet approaches the stick at 800 meters per second and leaves at 300 meters per second in the same direction. What is the angular speed of the intact spinning stick after the collision? Ignore air resistance.
First, let's review some concepts. Torque is defined as the tendency of force to rotate about a pivot point. It occurs only when a perpendicular force is applied to the lever arm, which is what is stated in the problem. If there is a pivot point, there must be a torque. If the force is angled, take the perpendicular component. Now, angular momentum, which is the rotational analog of momentum. It is defined as the moment of inertia times angular velocity, or the radius times mass times velocity. If we define a system, angular momentum will be conserved.
In order to solve this problem, we need to define a system so that we can use the law of conservation of angular momentum by having the net external torque be zero. Torque is defined as the perpendicular force that acts on an object with the pivot point. The net external torque is zero by having the system consist of the bullet and the rotating rod. The question mentions to neglect air resistance. Also, there is zero torque acting on the rod from the Earth's gravity because it is acting on a uniform rod's center of mass, which is the same as its pivot point. Any effect of gravity on the bullet can be ignored because the bullet is extremely fast and because the direction of the bullet's momentum does not change. The law of conservation of angular momentum states that the total angular momentum of the system immediately before the bullet strikes the rod is the same as the moment after it strikes the rod. We can split up the total angular momentum of the system to its component parts, the bullet and the stick. Because the rod begins at rest, the initial angular momentum of the stick is zero and can be removed from the equation. A common misconception is to use only the bullet's linear momentum when solving the problem because it is moving in a relatively straight path. However, we cannot combine angular and linear quantities into a singular conservation equation. Thus, we look at the moment immediately before the bullet perpendicularly strikes the rod and multiply its linear momentum by its distance to the pivot point to obtain its angular momentum.
The angular momentum for the rod rotating about a pivot point is defined as its moment of inertia times its angular velocity. As previously mentioned, the angular momentum of the bullet with respect to the rod's pivot point is its linear momentum multiplied by its distance from the pivot point. The moment of inertia for a uniform rigid rod with a pivot point through its center is 1/12 times the mass of the rod times the square of its length. This term can then be substituted into our equation. Values for most of our variables were provided within the question. The mass of the bullet was 4.0 grams, the initial velocity was 800 meters per second, the final velocity was 300 meters per second, the mass of the stick was 16.4 kilograms, the length of the stick was 2.0 meters, and the radius was 0.5 meters. We substitute these terms into our equation. We plug these values into our equation. A common mistake would be the inconsistency with units. The mass of the bullet needs to be converted to kilograms. Using algebra, the angular speed of the spinning rod was found to be 0.18 radians per second. Note that although radians does not appear in the equation, the standard unit for angular speed is radians per second. The answer was rounded to two significant figures.